Hello everybody. So this video is about me and my friends semester project this year. This was our Capstone project and we've been doing this under Bennett University's Computer Sciences department. So let's begin. We tried to target a problem which is not widely targeted by undergraduate students. We wanted to do something different. So let's introduce it. So radars, as we know, have been around for a long time now, probably more than 100 years. Someone filed a patent in 1905 in Germany for a radar. That was the first patent available. Since then, radars have been used in World War II for tracking airplanes. Since then, we have seen their applications in aviation, defense, and now in automotive industry like cars like Tesla. So they can detect objects that are far away in almost all weather conditions. Okay, a lot of focus have been dealt in detection. As you can see, there is an old radar that is just shows a target. It is there or not. Later, some advancements, and we are able to track the object as well, but not much more than that. So there's a classification gap. For example, the radar signal cannot tell the difference between a jet plane or a commercial private plane if they're the same height and same speed. So let's talk about something that is more interesting to us: ground surveillance radars. We want to check the moving objects on the ground: people, animals, cars, low-flying birds, etc. Out of all the classifications, differentiating between animals and humans is the most difficult task, mainly because they're similar size, speed, and the motion type. So animals have they walk on 4 legs, and so do humans have 4 extended body parts that you cannot classify it using just the radar signals, just by manually seeing them, and you cannot tell the difference between them. So we wanted to target that specific problem. You can ask yourself, why not use cameras? So cameras are being used right now, but they are a complementary solution. They require an operator to look in a particular direction and try to find out where the signal is being bounced from, and they try to classify if it is a man or an animal. Cameras, you can all probably guess, they have key limitations. You can as you can see in this picture, it is a foggy environment, and cameras have a particular range. They cannot look beyond the fog, and their field of view is quite narrow. They also perform very poorly in night and bad weather conditions like rain, fog, maybe in a dust storm and something like that. So it is quite difficult for a camera operator to manually classify whether it is a human or an animal just by looking at it. We took this opportunity and tried to explore and innovate new approach to the radar human and animal classification problem. Before we begin to the solution, just a quick overview how ground surveillance radars work. So we have a radar and an antenna that transmits an electromagnetic signal which hits a target, in this case a person, and it returns back. But you notice there is a Doppler shift. It is a physical and natural process which happens with every electromagnetic wave. If a person is walking towards the radar, then the Doppler shift is positive, and if he is walking away from the radar, then the Doppler shift is negative. Okay, so how do we view the Doppler shift? So when we get the radar returns, we can look at the spread of the signal that is being bounced back. So on the x-axis, on the x-axis, you have the frequency or the Doppler bin. On the y-axis, you have the power, that is in your decibels. In this example, we can see that this is an example for an animal walking. So there's a peak in the middle that is clearly visible, and marked as you can see. Uh, and there is also a peak in the beginning, which is just the noise, which we are not interested in classifying. So the noise can be from your trees, bushes, or any low-flying bird, and something like that. Maybe rain. Maybe rain falling can also produce some Doppler shift. Okay, so in this snapshot, so if we take 32 snapshots and put them side by side, we get a spectrogram, which is another representation, which is actually the heat map of an animal walking. So the data we have is a raw 32 cross 128 matrix, which includes the radar signals received by the ground surveillance radar, and previously we showed its visual representation. So there have been earlier attempts in classifying the human and animal, but the current performance they have is not at the market standard. They have a limited performance, and mostly the attempts use signal processing and other statistic models, which is not very robust and have a lot of error in them. Along with the radar signals, we have taken the geolocation, where was the signal being recorded, and we have the type of SNRs. SNRs are basically a signal to noise ratio. So my friend Shamuk will be explaining how our approach and what results do we have and what improvements we have done to the previous existing models.
This is Shanmuka, and I would like to tell you about the solution which we use to solve this task of classifying the radar signals as belonging to humans and animals. As you can see on the screen over here, you find that these animal radar signals and the human radar signals differ a lot to the human eye. But then when it comes to the raw data, they appear just as any other three-dimensional matrix of complex numbers. So we had to pre-process these complex three-dimensional arrays into real matrices. So there are four steps involving this pre-processing. Once I'll just go through that. First, we do hand smoothing. That is, we pass this data through a Hanning window, and what this does is it reduces the leakage during the Fourier transform. And after Hanning window, we pass it through a Fourier transform. In this case, we applied a discrete Fourier transform, and after Fourier transformation, we wanted to enhance the matrix. So the center elements of the matrix were replaced with the largest values of the matrix. And after that, the complete matrix is normalized. And finally, we have our data, and which upon plotting will be represented in this way. So coming to the model which we used, we applied a convolutional neural network. Initially, we designed a basic model, which was only 5 layers, and this didn't give much accuracy, and it was performing with around 60% accuracy. And this took only the input of just the complex array. But this is the you can see on the screen here the architecture of the baseline model which we use, and it wasn't performing really well. So we had to do some hyperparameter tuning, and we increased the number of layers and neurons, and we added some dropout values, etc. And we came up with a new model. It had approximately a million trainable parameters, and on training that with the this model actually consists of two different neural networks which are concatenated. So this is a pretty new method of classification. I'll just show it to you. Over here you can see that the data is split into the actual array of complex numbers and the categorical features. So we had to separate these two features and pass them to different neural networks because there was a shape dependency. So the shape of the matrix was a three-dimensional shape, whereas the categorical features are just a 0 or a 1 after binary encoding. So the array was passed into a neural network, convolution neural network, which has 13 layers, and the categorical features were passed into ANN of 2 layers, and then these two were concatenated to come out with a single value that is able to classify it as a human or an animal. And over here you can see our the epoch accuracy. We trained it over 30 epochs, and we were able to achieve this accuracy, like the model's performance. You can see it here. This is not an average epoch accuracy. This is specific to one particular run session. And the orange line describes the training performance, and the blue is the validation performance. And you can see that the epoch loss has also dropped from a lot. Initially, it was starting with 1, or I think 1.5, and then it came down to 0.15 or something. And since this is a task of binary classification, we needed to evaluate the model. And the best model, the best way to evaluate the performance of a model in binary classification is using the AUC ROC curves. And in this evaluation, we got around 0.989 of AUC. So this is a pretty good AUC in my opinion. So and on taking an average of all the runs and calculating the AUC and taking out the averages, we were able to achieve 0.99 validation AUC. So this method of concatenating two neural networks and using it to classify this radar signals was a great success, and it was performing a lot more better than the baseline convolutional network. And that's it. This is our solution, and we would like to come up with new solutions and new such projects in the future.